talk, or also raise your hands at the end of the presentation as well. So thank you very much. The floor is yours, at least.
Thank you. Thanks, Sandrine. Yeah, it's a bit odd. I mean, I'm not really into big awards and anything. And actually, the Leibniz Prize is much better than the Nobel Prize because we get money to do research. And I'm still as poor as I was before, but now I have money to do some research, which is really good. So I'm going to talk to you today about pushing the limits of atomic scale analytical microscopy. The reason why I didn't put atom probe right away in the title is mostly because it would mostly deter people away, and I want to talk about how we can use atom probe in conjunction with all the stuff, and you'll see a little bit. It was really quite timely that this talk was planned because we're trying to set up a new facility at Imperial, which might be of use to many of you in the future. So I'll touch on this in the second or third part of my talk. So as Sandrine was saying, I work primarily at the Max Planck Institute für Eisenforschung, which happens to be on Max Planck Straße in Düsseldorf, somewhere in the west of Germany. It's a dead ugly building or set of buildings. And just to give you a clue, that's what it looks like from the entrance. That's where I do atom probe, or at least I pretend. You can see that my lab coat is quite white because it's not been worn very much. That's where we do Eisenforschung. Eisen means iron, so it's research on iron and steel. So we can synthesize material and, make blades if we want. I can't really do that. And that's the group a couple of years ago. So the group is pretty chunky. There's about 20 to 25 people. We share quite a number of postdocs and students with other scientists at MPIE. So it's a bit difficult to know who belongs to which group. When I started, we were equipped with 2 atom probes and 2 focused ion beam to make specimens. I'll tell you a bit about this afterwards. And then we removed the older atom probe, and now we have 2 of the newer generation, plus the third one there from 5 years ago. And we added a plasma FIB, which again, I'll talk about afterwards. And within the Institute, we have a couple of aberration corrected TEMs and a couple of other more conventional TEMs and SEMs and all of this. So we're actually really quite well equipped to do stuff and play, which is quite fun. So the group has 2 main focus, I would say. So pushing advancing microscopy techniques and a strong focus on and looking at the way they are structured at the nanoscale. And in between, we try to use simulation, not necessarily led by me, but led also with collaborators to try and bridge the 2 aspects. So we work in engineering alloys, and that's the theme that I belong to at the materials department at Imperial, working on superalloys and steel and titanium and aluminium. My ERC consolidator was to look at hydrogen in materials, and I'll get back to some of this afterwards in more detail. And here again, I have some strong ties and collaborations with Ben Britton and Dev Dye. And also, we have some activity around catalysts and nanoparticle for catalysis, and which is also part of what's funded by the ERC. And over the past 2 or 3 years, we started a bit more of a stronger activity around magnetic materials and thermoelectrics. So I'll talk about some of these things, not all of it, but I'm happy to answer questions or have further discussions with whoever is interested at the end. So materials that we tend to consider as one big block is actually, they're quite complex typically. There's a hierarchy of different structures and of the way the atoms are arranged with respect to each other. This makes these small crystals that on a bigger scale become grain. All of these grains can have different orientations and joining each other. There's what we call these grain boundaries, which are basically locations where stuff can happen. And then the distribution of atoms of different species within these materials can be also very complex. And all of this combines to provide the material with certain properties, so physical properties, mechanical properties, and that's why they're made. That's because they're supposed to be useful. So we want to see how we can understand how this hierarchy of structure and composition actually forms, and how it makes these materials, it provides these materials with a set of properties. Typically, the problem is that every technique that you can think of to analyze materials will have a number of limitations. So in terms of how sensitive they can be to measuring composition, for example, how precisely they can measure the position of different atoms or the structure. And there's no single answer to these questions. When we start looking at a material, we can start very big, but sometimes we need to go to very, very tiny details. And there's a zoo of different techniques. Some of them will be useful for some things, some of them will be useful for other things. And we always have to think about them in coordination. Well, what can we use to complement that other technique? And the way research is sometimes structured is that, I am quite good at doing atom probe tomography. Some other people might be very good at doing XPS or TEM, but we tend to not always talk to each other. We sometimes tend to hate one another and say that the other person is doing shit. And that's really not the way we should think about these things. We should think about the possible handshaking for across many scales, across many sensitivities. We can all complement and put together the big picture. And where atom probe at the moment is really quite useful compared to other techniques, it's in its capacity to look at light elements. So when we think light, we might think, lithium and carbon and boron, and potentially there's also the possibility to look at individual hydrogen atoms. So this doesn't come without idiosyncrasies and complexities, and I'll talk about this a little bit later as well. Effectively, what atom probe is really good at is to look, if I take a piece of this light steel, so it contains quite a bit of manganese and aluminum, and we put this at high temperature, we quench it, and it forms an FCC structure, face-centered cubic structure, and inside form carbides that are fully ordered. So here you can see this austenitic FCC matrix, and on either side you have this beautifully ordered structure where all of the atoms come and occupy a certain position in a way that makes this structure very beautiful in the TEM, but also it provides strength against the displacement of dislocation. So it provides strength to the alloy. But the problem with the TEM here is that it's a projection microscopy system, so you only see through the entire thickness of the specimen, and we don't really know where the carbon is sitting and where the manganese is sitting and where the iron is sitting. And by combining this transmission-electron microscopy to high resolution, where we really see the structure, with the atom probe, where we can go down to seeing the composition of all of these different objects, there we get a more global picture, a more holistic picture of what is inside of the material. And that will help us understand how these carbides, for example, grow over the course of the aging treatment, or when we start pulling on the material, how does the deformation affect these particles? So there's some sort of a match made in heaven between high resolution STEM or TEM and atom probe. They sort of talk on the same scale and have highly complementary analytical capabilities. So I'm talking about atom probe, and it's very obscure to most people, and that's probably normal and quite lucky, because now it gives me a job. So I'm going to now backtrack a little bit and get back to how the technique works. So the technique is underpinned by the effects that intense electric fields can have on matter. So if you consider a surface and an atom sitting on that surface, and if I apply a very intense field, electric field of maybe 10 to the 10 volts per meter, these surface atoms become rather unstable. They're not very happy under the strength of the field. And so they start to dissolve. And as they dissolve, they typically lose one electron, sometimes two, sometimes a bit more. But typically they will lose one. And then as they start to move away from the surface, or maybe I could do this. Oh, what a genius. So it's moved out, it transformed into an ion, and now you have an ion, a positive ion in an electric field. So the electric field will contribute to just push this ion away from the surface. And so you have a projection of the ions that have been created, and as they travel away from the surface, then they can undergo further ionization. This combination of field-assisted desorption and ionization is called field evaporation. So it is a thermally assisted process, so it's not completely wrong to call it evaporation, but typically it's really induced by the intense electric field. So this needs to be borne in mind. And again, typically to remove almost any atom from a surface, a field of 1 to 6, 10 to the power of 10 volts per meter is sufficient. So we don't get these very, very, very high charge states that you can find in some higher intensity or high energy physics experiments, but we still get charge states that are typically 1 to maybe 4, and that will depend on the ionization energy of the atoms that are departing from the surface and the underlying surface. So how can we reach fields that are that intense? I mean, you could put a gazillion volts in between two plates, right, that you put very close to one another. But electrostatics is actually quite nice with us because if we look at the field that you can create on a sphere of radius r, it is the voltage that you apply divided by the radius. So if we make a very sharp needle, and at the end of the needle, we have something that is more or less a sphere, or a spherical cap at least, then the fields that we can generate at the apex of the needle is more or less this, F, the voltage divided by the radius. There's a constant here, which is not really constant, but that is, we typically assume as constant, and that will vary from specimen to specimen, from something like 3 to something like 6. So basically, if I apply a few kilovolts of voltage on a needle that has a radius of curvature in the range of 100 nanometers, I will very quickly reach the 10 to the 10 volts per meter that I need to remove these atoms from the surface. So how do I make a very sharp needle? Typically, these days, we use the FIB. So here, I'm interested, for example, in this grain boundary. So I will cut a trench with the FIB, and then I flip the stage, and I cut another trench on the other side, up until the point where I've left this small bar in the middle. It's free underneath. And then I will cut it on one side, and now I'm left with a cantilever. Inside of the FIB, there's a micromanipulator, which is more or less a needle, and I can glue it with the gas injection system to this cantilever and make it free. And then this bar, I'm going to cut into small parts, like Toblerone type pieces, onto a support, and then I'm going to shape it as a needle. With all of this is done with the ion beam inside the FIB. So now I have a needle that has the right dimensions. I'm going to put this needle under ultra-high vacuum conditions and at low temperature, typically between 20 and LT Kelvin. And then I'm going to apply a high voltage, position this needle about 40 microns away from a counter electrode. And I'm going to apply the voltage increase the voltage up to the point where the surface atoms are starting to ionize and give back these electrons and start to fly away. And then we fly away following trajectories that are actually well determined because they are caused by the distribution of the electrostatic field. So all of this can be in principle calculated rather accurately. And then we have a detector system that will collect all of these ions one by one. So the detector is a combination typically of a set of microchannel plates and an anode. The microchannel plate will take this ion impact and turn it into about 1 million electrons. And the anode is going to collect these electrons and record the position of the impact. Then what we can do is control the time at which this field evaporation takes place. As I said, it is a thermally assisted process, so I can use laser pulses, for example, to very temporarily increase the temperature of the specimen above the cryogenic temperature at which it's held. And this will provide a small kick for the surface atoms to leave. Or I can increase the field while maintaining the low temperature, can increase the field by applying negative high voltage pulses onto the counter electrode. So when the high voltage pulse arrives to the electrode, it generates an opposite outside field right there at the surface of the needle. So temporarily increasing the field, so I facilitates the departure of these atoms in the form of ions right at the top of the pulse. By doing so, I can actually control the time when the ion leaves, and I know when it arrives on the detector. So I can use that time of flight to deduce the elemental nature of the ion that has flown. So I'm just basically doing time of flight mass spectrometry like many other techniques are using. And then by using some magic, which I'm going to detail afterwards a little bit, we can build a tomographic reconstruction. It's a point cloud in which every point here was one single atom that was detected, or an ion that was detected. And then we use the sequence in which we detect ions to reconstruct the depth. And the lateral position is given by the impact position, because as I said, we know how these ions are flying from the specimen onto the detector. So the results from an atom probe analysis is first a mass spectrum. So we get peaks pertaining to all of the different atoms or elements that are in the material initially. If I zoom in here, I can see that we even have isotopic resolution. So I can see here the 3 isotopes of chromium. The vanadium here is in between the isotopes of chromium. It's in the 2+ charge state. There is an isobar between chromium and iron. So there's an overlap, and it doesn't make our life always very easy. And then here again, we have the 1, 2, 3, 4 isotopes of iron with manganese in the middle. So this is a piece of steel. So there's always a bit of a zoo of different elements in there. And as I said, we get these detector coordinates and this time. And what we want is to translate this into this XYZ mass. So the mass is given by the time. What I'm going to just detail briefly is the way we do the transform between the sequence in which we detect ions and the detector coordinates into this XYZ coordinates of each individual atom. So the first thing we do is that we assume that our specimen has this spherical cap that is emitting an ion. This ion is detected, and we assume that it flew straight from the surface onto the detector, or at least using a projection model that we know. And so we can use an reverse to take this ion position and put it back onto this virtual emitting surface. Every time I do this, I will just move this virtual emitting surface down by just a tiny amount. And this is an assumption that sort of makes sense, because if I have 2 atoms, one on top of the other, the one that is below inside of the material basically will never field evaporate before the one that is at the top. So we can just make this assumption that it's not completely rubbish to think like this. So then I'm going to take the next atom and put it down, and then the next atom and put it down. And so the XY position comes from the reverse projection of the impact position, and the Z comes from simply the progressive incrementation of the depth. On normal instruments, we get a resolution, an efficiency, of detection that is the same across all of the range of mass to charge ratios. But because we are not detecting all of these ions, when we move the emitting surface down, we just move it by a little bit more to account for the fact that we are not detecting all of the ions. So this process seems awfully simple, and it is, and it's probably simplistic. In some cases, we have issues and stuff, but it actually works quite well. So there are a few limitations in the data, which don't prevent us from doing our job, but we need to be conscious that it's not all fun and dandy at times. So again, if I look at this specimen surface, when I take a spherical cap and I intersect the spherical cap with atoms that are organized on a crystalline lattice, typically we are going to end up with a series of terraces like this. And when I apply the voltage, and this voltage translates into a high field, there is a certain distribution of the field, and the atom here at the edge of the terrace will not be subject to the same field as its neighbors. And this very specific distribution of the field at the edge of the terraces means that the atoms don't tend to fly really straight like this, but they tend to have slight aberrations in their trajectories. And again, as I've just mentioned, we don't detect all of the ions. Some of them are lost, but it's not based on their mass to charge ratio or Z number, like it can be in other techniques. It is depending on where they land on the micro channel plates, because the micro channel plates are just a series of tubes. So if you end up in between the tubes, you're lost. So when we start with a specimen that has a beautiful crystalline structure like this, this is a simulation, by the way, we can end up with something that's a bit more of a mess. But that's okay, because we still have a resolution spatially that is unrivaled. So when we look at this piece of steel, I've shown you the mass spectrum before that we've analyzed. What we can do is look at where all of these elements are sitting inside of the data set. So how is manganese partitioning between this particle that happens to have a lot of carbon, and it's probably a carbide, and here the matrix, which in this case is ferritic. And I have also these elongated features rich in vanadium, which happen to be dislocations that are covered with vanadium. So that's where the atom probe is strong, is in this three-dimensional distribution of all of the elements. And we can actually go down to measuring the relatively precise composition of all of these species and all of the different objects that we are imaging. So for quite some time, atom probe was basically doing mostly metals. And so it remained a very niche technique. But in the past, maybe 10 to 15 years, it started to open to a lot more different applications. So we now have a pretty active section of the community that's looking at nanoparticles, for example. So here we have embedded the nanoparticles in a metallic matrix. And you can see they're there, and then we can go down to measuring the composition of individual nanoparticles like this. In that case, it's pure palladium, so it's really a bit boring. But still, you can see they've also almost maintained this sort of cuboidal structural shape. We've looked at these really odd, so it's a series of nanowires like this that make hollow structures, and so. Again, these are titanium dioxide. We could barely analyze these things, but they have very interesting photoelectrocatalytic properties. So we wanted to see what was happening on their surface, especially. And here I'm just highlighting the complementarity with other techniques. So here you can see it's just a TM, or scanning transmission-electron microscopy. Here we're looking through this specimen, and you can see this series of almost finger-like nanowires that have grown. And then our colleagues at MPIE did some electron tomography to make sure that these were really hollow, and we can see the beautiful hole in the middle. And then they went through some partial reduction of the surface of this titanium dioxide, and they could see a very significant change in their photoelectrocatalytic properties. And then we put those into the atom probe, so you can see they're pretty big for us. I mean, they're more like 200-300 nanometers in size. So we filled the hole in the middle and embedded these nano objects into a metallic matrix, made needles exactly in the way I've shown before. And now we can look at what's happening here at the interface of the nanowires themselves. So the nickel is just a matrix that we've added. We end up with something that's rather close to TiO2. And what we detected is a range of different species segregated at the interface, so sodium, nitrogen, boron, which typically would be extremely challenging to detect by any other technique, because the sensitivity of X-ray-based techniques, for example, or of TEM-based techniques typically depend on the Z number. So getting down to measuring 0.2% of boron at an interface can be extremely challenging. But we could see this, and actually by looking through the literature, we could also see that some of these impurities might help stabilize the oxygen vacancies that are at the surface of the nanowires after the partial reduction. So this was quite interesting. We pursued also some other types of weird structures for us, like these 2D MOS2 nanosheets. So in that case, you can see these are agglomerates of two-dimensional sheets containing moly and sulfur. And by TM shows that there are a couple of different structures, and the doping with rhenium actually in principle might stabilize one of these structures a bit more than the other, and they don't have the same activity with respect to catalysis. So we embedded these again in nickel, and we could do the atom probe analysis. We could go through this MOS2 stack of MOS2 sheets. So we don't have the perfect atomic resolution that you would get in the TEM, but we could already reveal that the rhenium, for example, is not segregated at the interface, but is partitioning where the moly is also there, right in the core of this set of 2D objects. And again, we could detect some oxygen and some nitrogen and some carbon, which would be very difficult to catch with any other technique. And this, we also saw that they were really within the 2D stack and not right at the interface. And we think they come from the synthesis. We could also detect significant amounts, maybe 1%, 2% of tungsten or vanadium that are coming from the molybdenum precursor. All of these different species that are inside of the material at the end of the day would affect its properties, its long-term longevity, aspects that typically are never discussed in papers dealing with these materials, mostly because we can't measure this with any other technique. And getting to the point where we can get these results, it's actually quite recently that we can do these types of things. And still not straightforward, by the way. But that gives you a little bit of a flavor for what the combination of the the atomic structure we can get from the TM combined with the compositional measurements that we can get from the atom probe. That's where the strength lies. It's not in just one or just the other. It's really in the combination of the two. So up to now, I've mostly talked to you about more or less conventional atom probing, or stuff that we've been able to do almost anywhere where there's an atom probe, which is, there's about 100, I think, in the world at the moment that are active. And to give you an idea, when I was a PhD student about 15 years ago, there were about 20. So there's a very strong rise in the number of people who are using the technique, which is good, but also in terms of number of things that we are trialing. So a very big problem that we are trying to work hard to try and tackle with the atom probe at the moment is the issue of hydrogen embrittlement, and more generally of what hydrogen does inside of a material. So if we take an engineering superalloy, so typically alloys that are used for high temperature applications that contain quite a lot of different elements. And if you pull on a piece of this material up until it breaks, I can deform it to maybe about 40 to 45% of its length before it breaks. But when I charge hydrogen inside of the sample and do the same test, it breaks at about only 10 to 15%. So what does hydrogen do to cause this? And there's many questions around these problems. So this is one of the aspects of what is called hydrogen embrittlement. And there are many mechanisms that have been proposed. I mean, you can read all of these beautiful papers from Rainer Kirchheim, where hydrogen will go in, and then it can interact either at the surface, it can interact with vacancies, it can just be in the matrix somewhere as an interstitial, it can interact with dislocations or with grand boundaries and interfaces. And all of these things, all of these possible interactions can lead to different ways where the hydrogen is going to affect the physical properties of the material, and particularly its mechanical behavior. The problem with all of these possible mechanisms is that we don't know where the hydrogen is inside of the material. When it starts making a large-scale phase, a hydride, then we can see it often when we look at the right resolution. But even when it's not in a phase, when it's spread across the material, we need to be able to see and quantify where is hydrogen inside of the materials. atom probe is in principle capable of looking at hydrogen. We can measure where the hydrogen, how much the mass of hydrogen is not a problem. So we can go and measure how much hydrogen is inside of our specimen. We can even see where it is located inside of the microstructure. Is it in one specific phase? Is it located at some of these dislocations or at an interface? But the problem is that if I take any commercial atom probe or homemade atom probe, there's always hydrogen in a UHV chamber, right? You can do what you want. The stainless steel that is used for these different chambers always contains quite a lot of hydrogen that keeps dissolving for the entire lifetime of the chamber itself. So the people selling atom probes would tell you that your atom probe is going to get better over time, and it might take 10 years, and you will have lost maybe half of the hydrogen from your runs. But when you have hydrogen in the chamber, because our specimen is very cold and under a high field, the hydrogen will come towards the specimen surface, stick to it, or just be driven towards the apex and then be ionized and then be detected. So any data set that we acquire always has some level of hydrogen. But this is not the hydrogen I'm looking for, right? It's not the droid I'm looking for. The droid I'm looking for is the hydrogen that is inside the specimen at the beginning of the experiment. So we need to find a way to get away from this hydrogen is always there type situation. Also, we started putting together some infrastructure for this, and then we realized that even the preparation of the specimens can lead to the introduction of hydrogen. So we took some commercially pure titanium. There's been worked on, for the past, 50 years on this, where when you polish it even mechanically or with the FIB or electrochemically for making TM lamellar, in commercially pure titanium tends to form these elongated needles that are actually titanium hydrides. And this can come from just water that is inside the solution when we're polishing, or water from within the FIB, for example, or just when we are doing the electropolishing in acidic conditions, some of the hydrogen from the acid can go in. So when we started doing atom probe of these things, we found these beautiful hydroids. We were really not expecting them, so we had to go back through the literature to understand what was happening. But basically, we could almost half, if not 2/3 of the specimens that we would make would contain a hydroid. And when we want to look at the hydrogen that is inside the material before the preparation, then it was a bit of a problem. So we're in a bit of a pickle there. So we looked at a range of different alloys and a range of different conditions. So titanium has two different phases, an alpha HCP phase and a beta, which is BCC. And looking at how much hydrogen we would detect after the preparation with the FIB. And often we would find these hydrides or these hydrides here at an interface between alpha and beta. And even when we could not find hydrides, we sometimes saw that's a TI6246 that we were looking at with Dave Dye's group. We could see large amounts, maybe 15-20% of hydrogen inserted into the beta phase. So again, if you want to look at hydrogen, it's a bit of a problem when you put so much hydrogen inside of the specimen during the prep. So at MPIE, we started building a capacity, as I said. So we had an atom probe, or in that case, 2 atom probes. We have a glove box, this plasma FIB that I mentioned earlier. And what we wanted to do was find ways to transfer samples cleanly between the glove box, the plasma FIB, and the atom probe. So we purchased a UHV suitcase, and we all joined this together in what was coined the Laplace project. I could explain why Laplace, but for now it's probably not very useful. And so we put all of this together, developing ways to transfer everything from one platform to the other, everything at cryogenic temperature. And when we use our plasma FIB at low temperature, so at cryo minus 130, minus 140 degrees Celsius, we prepare specimens and we don't find any hydrides. If we do the plasma FIB at room temperature, we find hydrides everywhere. If we do the gallium fibbing at room temperature, as I said before, we end up with these hydrides everywhere. So it seems that going cold is already a first step towards making things a bit cleaner. And again, if I look at this 624C alloy, that's the type of hydrogen concentration we would get, typically about 15, 16% in beta. And in that case, we find 0, or more or less just the background, which comes from the microscope itself, which was already a good sign that now we are clean, we might be able to charge or put more hydrogen inside and look where it is. So we proposed a mechanism to explain why the going to cryo temperature helps. And we believe that it's mostly due to a lower diffusivity of the hydrogen inside of the structure at low temperature. And as we keep otherwise making the specimen smaller and thinner and thinner and thinner, we are artificially increasing otherwise the concentration of hydrogen to a point where it becomes more favorable for the hydrogen to form another phase, the titanium hydride. So we started playing around now with charging this alpha beta alloy 6246. So we did electrochemical charging. So you put a small piece of the material in a solution and you apply a voltage, and that solution contains, in that case, NaOD. So we are in alkaline solutions with D2O. And why do we use D? Because in principle, D is deuterium, so the second isotope of hydrogen. There's less than 1% of natural deuterium when we have hydrogen. So if we introduce the deuterium inside of the specimen, we should see a peak at 2 Dalton, or 2 atomic mass unit per Coulomb. That should tell us basically that this is the hydrogen we've introduced inside of the structure, not the one that is inside of the chamber initially. And we've done this up to the point where we're starting to form hydrides, or deuteride in that case, and we could look at the way the different elements are redistributed and which phases are forming. And here we were actually really quite happy to see these hydrides and deuterides. It was actually forming during our processing and not just caused by artificially by the fibbing. And what we wanted to do was compare this electrochemically induced hydrides, which are very typically used to test the way hydrogen would affect the mechanical properties of a sample, with gas charging at elevated temperature, which is probably much closer to the way hydrogen embrittlement would take place during service of these types of alloys that are used in plane engines. So there will be a pickup of hydrogen at high temperature, and this could potentially cause the nucleation of hydrides, for example. But the hydrides we're going to form at 600 C are not the same one that we would form at room temperature during electrochemical charging. So in that case, again, we did some atom probing. We ended up with a fully deuterated material, and we could see a redistribution of aluminium, for example, forming some titanium aluminium phases. Where the aluminium is rich, hydrogen doesn't really want to go. They don't really like each other. They're not good friends. But the interest of doing it at higher temperature is that you can start to assist to the diffusion of other elements than just hydrogen. So in that case, we could really see new phases forming and new deuterides forming, for example, that we were not really expecting. So this is all ongoing work. So we don't have all the answers yet, but we are already in a position where we can look at hydrogenated or deuterated systems and go down to measuring the composition of these different phases and try to understand how this relates to the mechanical properties. So to finish, what's happening at Imperial? So Imperial got, like maybe a month ago, 6 weeks ago, we got the results from EPSRC that we would be in a position to buy an atom probe and a big TEM, and the capability to have, again, one of these glove boxes that we can use as a hub to transfer specimens at low temperature between the TM and the glove box and the atom probe, and a FIB as well, which we're going to get as part of this facility, with the idea to reproduce a bit what we've been doing at MPIE, just better. And there's also a potential then to link to some of the more large-scale existing infrastructure that is at Imperial, so this multi-beam SIMS or the XPS facility, with the idea that we're going to generate a whole bunch of data that we won't be really in a position to analyze globally, and maybe later, there could be potential for integrating all of this data in clever ways and find ways for the different techniques to talk to each other. So this is led by Dr. Finn Giuliani and a slightly older Mary Ryan and Alex Porter, Stella Petrozzini, and Katerina Markvart. And so we're going to start building this up over the next probably 12 to 15 months, with the atom probe being planned to be delivered, I think, at the end of Q1 next year. So after installation and everything, probably mid next year, we should be in a position to start doing some of these experiments in London. So examples of where this combination of atom probe and TM has been used in the recent years that I was involved with. Here, for example, is the combination with XPS, where we looked at this surface of iridium thin films after the oxygen evolution reaction and the way the surface oxide is forming with these intermediate oxides forming that are not really iridium anymore and not really IRO2 yet. They're somewhere in between. And so we could go down to combining this, the TM and EELS, so electron energy loss spectroscopy, with atom probe to get an idea of what was the composition of these layers during the OER as it was evolving. Again, we could look at potentially stable hydrides, which can be used for hydrogen storage. So hydrides can be used, for example, in submarines to provide long-term energy storage. And here we can combine this with EELS again, where we can see the different phases. We can identify the nature of the hydride through EELS and through the atom probe. So again, here it's really the handshake with the other techniques that is going to be really quite fun. We also looked at a bit at MPIE at some of these ugly and very dirty organic perovskite type things. So we tried to make atom probe needles and TMMLA from these rubidium doped samples. And at room temperature, the gallium FIB was breaking down a ton of stuff. So what we would be getting from the atom probe was really messy, and it was really difficult to identify all these different fragments. But after cryo-FIBing, we could actually get to the point where these peaks sort of made more sense. And we noticed that a significant difference, most likely associated to much less beam damage that was induced by the fibbing. So again, it's something that we don't have a huge amount of experience with at MPIE, but I think there's much more interest across London to use these types of facilities. And last, but maybe not least, over the past 6 months, we've been trying to, because we can do everything at low temperature, in principle, we can just look at ice. So we took heavy water and turned it into ice by plunge freezing in liquid nitrogen on a flat substrate. And then we used the FIB to dig a trench all around and make a needle out of this. It's pure water, so it's a bit boring, but we could see these peaks corresponding to different clusters or molecular ions containing more than just one molecule of water. And in principle, it can be used now as a medium to carry other objects. So, for example, we could potentially look at nanoparticles that are being formed in a solution, or during an activation of when they're used to catalyze a reaction. In principle, we could find ways and workflows to take a small volume of the solution and then turn this into one of these needles, and then look at the distribution of the different species with respect to the different nano objects in the solution. So I think there's a bright future for these types of applications. Yeah, the paper will be out soon. If you have questions on this, just let me know. Anyway, so that's where we stand. Atom probe tomography is a compositional mapping tool. It's got better than a nanometer resolution in XYZ. It works with almost everything that's solid enough. If it's just individual objects, we need to embed them in a matrix, but in principle, we can still look at them. It's not as straightforward as people might think. There's a bit of tricky physics underpinning the way the atoms are removed from the surface. When there are covalent bonds, for example, sometimes we don't get individual atoms, but we have molecular ions coming off, and we need to understand a bit how they form, just to make sure that we don't bullshit our way through an interpretation. But it's still extremely valuable, and especially it provides information that you could very barely get in any other way on that sort of scale. So here, for example, we can measure the composition of particles that are 2 to 5 nanometers across in 3 dimensions. And I think the best conclusion I can say is that the world needs more atom probes. I've done my share of the work for this. Got 3 in Germany, and now that there will be 1 at Imperial, and we'll be able to start field evaporating all bits and bobs from there. So thanks for your attention, and I'm very happy to take any questions you might have.
Thank you very much. This is amazing. Okay, we have questions. God, I love the wand and the hat from Matthew.